Hello, and welcome to discussion 4 for CS61B. Today we're going to be talking about objects. So before we get into the actual review, let's talk about announcements real quick. A lot of these are out of date, but Project Zero is due Friday, the 11th of February. Make sure you get help on that. For that week, the lab is going to be project office hours, so there's no lab assignment. Make sure you also get the test 1 form in by that date for the first midterm. There will be an exam review session held that Friday from 2 to 4 p.m. in SOTA 271 in case you want some extra help studying for the test. And lastly, please make sure you're making use of Gitbugs. Trust me, it's faster to submit a Gitbug than to wait a few hours in the office hour queue right when a project is due. So moving on from announcements, let's get into review. This content's actually a little bit ahead of where we are in the class, and the reason we're covering it now is because the test is happening a little earlier than it would normally happen, and I want to make sure that in section and things like that next week, we have enough time to cover more of the problems for test review, so we're moving some of the mini lecture a week early. So what that means is you might not know everything we're talking about today, and that's totally fine. I encourage you to revisit this when you're at a point where you get it more. So we've already kind of talked about classes. We kind of went over them as a concept when we first got our introduction to Java. We know that all code needs to be contained within a class, but part of what makes Java so powerful is the sort of class structure. And what I mean by that is that classes aren't just individual. They can kind of exist in these families, where subclasses are classes that extend other classes and therefore have access to all of the variables and functions in their parent class, in addition to any variables and functions defined in the child class. And the opposite of that relationship is a superclass or parent class, which is the class that is being extended. So the classic example that's sort of this is more imaginary example is, let's say you have a dog class, right? So maybe dogs bark and they breathe and they play fetch and all of these other things. But you can also have these specialty subclasses. Here's a corgi, here's a pit bull. And each of them is a dog. That's kind of the relationship we consider when we're talking about superclasses and subclasses. We say it's an is-a relationship. A pit bull is a dog, but it has some extra features. Maybe pit bulls can defend you in a way that not all dogs can, so they have an extra function, or they override the function in the dog class that does that. So this is an example of a superclass-subclass relationship. A key thing here is that each class can only extend a single class, but a class can be extended by many classes. So Pitbull cannot also be a cat at the same time that it's a dog, but there are many kinds of dogs that all extend the dog class. Moving on, we get something called abstract classes. So now we're getting more interesting. Abstract classes are classes that cannot directly be referenced or instantiated. So you can't just create a new animal. Instead, they have to be extended by a concrete class. And they kind of describe the sort of things that this type of class should be able to do without providing necessarily a concrete implementation of that. So here in our kind of imaginary example, I have animal as an abstract class. And the reason I do it this way is because you gotta think about it. There is such a thing as just a dog, right? Like some sort of mutt that isn't really a purebred. That's just a dog. And there are purebreds like corgis and pit bulls, but I don't think there's any animal out there that would be best described as an animal. Every animal out there has its own set of unique features that come from being some sort of subtype of animal, right? So animal is kind of more of an abstract type. It's not really a concrete implementation of the idea that all animals have to have some way of eating, all animals might have to have some way of breathing, but each animal might implement that in a completely different way. So that's why we have abstract classes, but they still have to follow the other rules of classes, such as dog can only extend one thing, and that one thing in this case is the animal class. It can't extend another thing. And dog also has access to all of the variables and functions defined in the animal class, just like a normal class would have. Okay, next we have something that kind of muddies the waters a bit. It's called an interface. Now, interfaces are in practice very similar to abstract classes, especially in more modern versions of Java. So the idea about interfaces is that they kind of describe a single quality, a single trait, a single ability of the class that implements them. And so real life examples include things like comparable, like iterable. In this kind of fake example, we have squishable or photogenic, or maybe we'd have guardable. Anything that kind of talks about a single ability that that class has. And so interfaces have usually list out functions without providing implementations, and then whatever class implements them has to provide those concrete implementation. And that's what makes it similar to abstract classes. Now, in older versions of Java, only abstract classes have the ability to provide like a default implementation. In older versions, interfaces were physically not allowed to provide implementations. In more recent versions, like the one that you guys use, you can use the default keyword to provide an implementation within an interface, which kind of makes abstract classes and interfaces very similar. So there is some discourse about when you should be using either. We're never going to ask you about that. We're never going to ask you when should you use an interface versus an abstract class. You just kind of have to know what each of them does and sort of the implementational details of how to use either of them. And here are some more concrete keyword implementations. So for an abstract class, you use the keyword abstract, and then it's just the same as a normal class definition. For interfaces, you use the word interface instead of class. When you're extending a class, you use the extends keyword, whether that's for an abstract class or for a concrete class. And then when we implement an interface, you use the implements keyword. You can use that in conjunction with the extends keyword. And you can implement multiple interfaces. You can only extend a single class. Okay, now that we've gone through all of that, we will continue with the worksheet. If not all of that made sense, that's totally fine. We're going to go over it more next week, and then we'll have some problems that really get into the nitty-gritty of classes. This week, we're going to kind of keep pretty light on classes still. Okay, so our first problem is talking about this avatar class. And the question is, what would be printed after executing the main method? So for problems like these, I highly recommend that you write an environment diagram. Trust me, it's easier to keep things on paper than it is to keep them in your head. I'll give you a minute to try it out, and then we can go over it together. Okay, let's go over it. So like I said, we are going to be using an environment diagram. So first, let's do this first line, line 11. So in this case, this is the kind of way I like to set these things up. So we have our foo1 variable. This is the variable itself. It is the simple container that contains a pointer to our actual class, right? Because this is just a pointer. It's not the class itself like we talked about last week. And then within the avatar instance, we have a variable called fluid, which again contains another pointer to the string 2. I also like to keep this box in the bottom, which keeps track of all of these static variables for each class. And the reason I do it this way is because when a static variable changes for a single instance, it changes for all of the instances. And I don't want to end up in a situation where I change the variable in one place, but not the other places. So I solved that by just keeping all static variables in a separate location, categorized by class, and that way I'll never have to worry about changing everything. And then lastly, I have this little console area down here for our console output. This is what happens after we run the line 11, and then we'll run line 12, and you can see here that we have foo2. That's going to have fluid equals to 4, and our electricity variable has been updated to 3, and this update applies to both instances because it is a static variable. So when we print out foo1.electricity plus foo1.fluid, we get 3, 2. Next, we're going to run foo1.electricity equals I declare. And we're just going to update that down here. And again, that updates for both classes. And then foo1.fluid, we're going to set to 8 them war that only impacts foo1, not foo2, because fluid is an instance variable. And lastly, when we print out foo2.electricity plus foo2.fluid, we get I declare 4. And that is our final console output. So moving on, let's get on to 1B. So would this code still compile if we change line 2 and 3? And if not, what lines do we have to alter for it to work? I'll give you a minute to think about it, and then we can go over it together. Okay, so I hope you had a chance to think about it. So, like we talked about last week or the week before, maybe, static variables can be called on using either an instance of the class or the class name itself. So this line previously worked because electricity was a static variable, so you could call avatar.electricity. Now that electricity is no longer a static variable, this no longer works. However, this line is still going to be completely fine because, like we just said, you can call on static variables using an instance. That is totally fine. Also, both of these keywords are completely useless in this situation. You don't need this avatar electricity. You don't need the this and this dot fluid either. There is no ambiguity about which electricity or which fluid you are referring to because there isn't an electricity or fluid in that local scope. So there is no other variable defined within the constructor that has the same name. So your computer will automatically know to look for variables on the class level instead. This is something that's kind of different from Python, so it's something I wanted to point out. But yeah, this is what I just said. Line 6 will error. Line 7 is totally fine. You could fix it by getting rid of this avatar in avatar.electricity. Okay, last part of this problem, let's talk about 1C. So would this code still compile if we added this getFluid function? I'll give you a minute to think about it. Okay, so coming back to this, very similar to our last problem, it would not. And the reason is because it's a static function, right? So static functions only have access to the static variables and functions of that class. Because you can kind of imagine the logic here where if you tried to call on fluid from a static function, let's say we called avatar.getFluid, which fluid would we return, right? Every instance has its own version of fluid with a different value. So which one's the official version that would be returned by this function? There isn't one, so this would cause a compile time error because Java would see this and immediately just say, this isn't allowed, sorry, not happening. Okay, so now we can do another problem that's kind of similar. This is called a static shock. Basically the same idea. We have a main function, so what would it print? And I'll give you a minute to think about it. Okay, let's work this out. So first, in this line right here, we are creating this gear variable. And we are calling on this constructor for shock. We're passing in 200. So we're going to go through this constructor, which is why I haven't drawn this arrow yet. Because if you remember what happens in order when we have a line like this is this side of the function or this side of this equal sign is first evaluated. So shock is evaluated first. And then we assign it to gear. So this arrow won't exist until the shock instance has been completed. You'll also notice that all of the variables in shock are static, so you'll see that our shock instance actually doesn't have any instance variables of its own. So starting there, we are going to go to this dot bang equals num, so that's going to set bang to equal to 200. And then we're going to call on that starter function. So starter over here is a static function. So shock gear, we're having another gear. So I put a little parenthesis starter here to make sure that we remember that this is the version that is inside the starter function, creating a new shock. And this one is setting this dot bang to 100. Bang is a static variable, so that's replacing it for everyone. And then we're returning gear and setting baby equal to that. So this baby variable is equal to this shock instance. And then because we've exited from this scope, this variable ceases to exist, but don't worry, the instance that it was pointing at still exists because baby is pointing at it. And then we're going to set this dot bang to be plus equal to that num, so it's going to be set equal to 300. And now we're going to go to line 17, which is going to print out gear.bang, which prints out the static variable, so that prints out 300. And now we're going to run the shrink function. So this is the static shrink function right here. And it's taking in a shock, so we're passing in gear right here. And it's just doing static dot bang minus equals 1. So that sets our bang equal to 299 because it was previously 300. And next we're going into shrink and we're going to call starter and pass that into shrink. So first, let's create that shock instance again. Going back, all of this is creating a new shock, which sets the bang equal to 100 one more time, if you recall. And now we're going to go down here and it's going to subtract 1 from that, which is going to give us 99. And lastly, we're going to print out gear.bang again, which is going to set this value equal to 99. This is a little harder than the previous problem, but hopefully that all was easy to follow along with. Okay, let's get into some array problems because arrays are one of those core data structures in this class, and I really want to make sure we touch on everything here. So here in this situation, what we're trying to do is we're trying to implement reverse such that it destructively reverses the elements of array A. So destructively here means that we want to be reversing the elements kind of in place and we're not returning anything. So A is what we're going to have as our result. So I will give you a minute to try that out and then we will reconvene and talk about it together. Okay, welcome back. So we know the first element needs to be the last element, and the second element needs to be the second to last element, and etc. So what we're going to do is we're just going to go through the array and swap things, right? We're going to swap the first and the last, and the second to last, and third to third to last, and etc. So we only need to loop through the first half of the array because the other half will get solved as we swap. If we don't do this, we're going to end up swapping everything back, which is not what we want to do, right? So we only have to go until a.length divided by 2. Otherwise, it's a very classic for loop. And now we're going to do our swap. So we're going to set our temporary variable equal to the item that is I from the end back. And then we're going to replace that, what used to be there, with I from the front. And then we're going to replace I from the front with that temporary value. Again, this is a swap thing. We've seen it before in previous problems. If you're confused on how that works, I recommend you check out, I believe, last week's discussion where we did a very similar thing for linked lists. Okay, so our next problem is going to be reversing an array extra. So this time we are going to be reverse diagonal. So we're trying to reverse the elements of B, which is a 2-dimensional array, assuming it's going to be square, across the diagonal. So I'll give you a minute to think about how we could possibly do that, and then we will go do it together. Okay, let's do this together. So it's the same idea as the last problem, except it's across the diagonal. So the nth diagonal has n plus 1 items in it. I'm not going to show you how that's true. If you're curious, you can just draw a square and check yourself. But just trust me that it's true. So what we're going to do is we're going to iterate through the diagonal. We know that if we are going for the nth diagonal, then we want to go for n divided by 2 items. So we need to get the diagonal item. So that's going to be diagonal minus 1 and diagonal minus I and I. And on the other hand, the item that we are going to be putting there is I diagonal minus I. So basically swapping something with the item that is kind of the reflection of it, if you can kind of imagine how that would look. But other than that, it's just a pretty simple swap as usual. If this solution is confusing to you, I recommend you try drawing out some squares and kind of seeing how this is the case. This is kind of similar to doing a transpose, which we're actually going to do later in this worksheet. But next, we're going to do this circular buffer problem. So we want to implement overflow so that it non-destructively flattens a circular buffer. For this problem, I highly recommend you look at the worksheet because it is missing a lot of context on this slide. Primarily, there is the actual definition for array copy there, which is going to be super important. The general idea is we have an array, which the quote-unquote start of the array is actually at index I, and then it sort of wraps around the array to the back. And then, this sort of buffer is full. So we want to add a new item into it. We have to make the array bigger anyway, so we're figuring, why don't we flatten it out and then add the item? So I'll give you a chance to think about how that could be done, and then we will work on it together. Okay, great. Let's go over it. So first, we want to create an array that's bigger, right? Because it's non-destructive, so we can't be using the same one. I mean, even if it wasn't non-destructive, we would still have to do that because unlike Python and Java, you cannot make arrays bigger. Once you've made an array, that size is what's going to be until it dies. If you want to make a bigger array, you have to create a new one. Next, we're going to copy the beginning of the circular buffer. So how do we decode this? Again, if you're looking for the actual arguments to array copy, I recommend you look at the worksheet. On the exam, we will give them to you. We will not expect you to memorize it. But all it's saying is, okay, so we're going to take array A, starting from index I, and we're going to copy it over into array B, starting at its index 0. And we're going to copy over this many terms, which is a dot length minus I. That's the number of terms left in the up until we hit the end, because we don't want to go past the end of the array or we're going to have some errors. And just similarly, we're going to do the same thing, but for the end of the circular buffer, aka the beginning half of A. So we're going to copy from array A, starting from its 0th index, into B, starting from where we just ended off up here, so a dot length minus I, and we're going to copy up until I. So this is like the second half of our circular buffer. We're copying that into place. And now we just want to insert our new item at the very end of B, because B is of length a dot length plus 1. So this is the last element in B. And then we're going to return B, just like that. That's our new array. That's all it takes. Next, we're going to talk about transposing a 2D array for our last problem. Again, this is quite similar to what we just did in 3B, so I'll give you a chance to think about it. If you're not sure what a transpose is, I recommend you look it up. Don't worry, on the test, we will not ask you for things that require background in math without giving you all the information you need, but this is a discussion worksheet, so we have slightly lower standards. But yeah, give it a shot. Okay, welcome back. Let's go over it together. So, first things first, we want to iterate through all of the columns in our array, right? So here we have a dot length. We're going up to a dot length. We're iterating through all of the columns. And then we want to iterate through all the rows. We want to make sure that every single item is in the right place. We are assuming here that A is a square 2D matrix. It doesn't have to be, or not necessarily square. We're assuming that it is, well, I guess we are assuming it's square too. We're assuming that all of the second arrays are of the same length. But we are starting at j equals I, and then we're going until j is less than a dot I equals length. So what that means is that we're actually just iterating through the top right corner of this array, this 2D array. Not necessarily the whole thing. We're looking at the triangle that is the sort of top right half. And the reason we're doing that is the same reason that we did it we only looked at the first half for all of the other swapping based array code things that we just did. Because if we go through everything, we're going to end up swapping it twice. And so we're going to end up right there, right back where we started. So here what we're doing is we're only going through half of this 2D array, and then we're going to swap diagonally, which again is very similar to what we did in part 3B. AJI becomes AIJ and vice versa. And that brings us to the end of our worksheet for today. So thank you all for coming. Thank you for paying attention. Good luck on finishing Project Zero, and good luck on the midterm. Let me know how you do. And I'll see you guys next week. Bye.